Well, welcome everybody. I've got this fancy jacket on today, so I thought I should introduce our speaker. Martha Steenstrup. Martha Steenstrup is an adjunct professor here. She's been a real professor in various other places. Adjunct professors are real professors. Yeah. I can't remember. At Clemson, Clemson University in the South.
Yeah, in electrical engineering.
And but before that, she was at BBN, which is one of the original people that made the internet, the ARPANET. And she used to brag that she could bring down the whole internet.
In those days.
Why didn't you? And then she got into abstract mathematics. And
no, that was before, but never mind. Yeah.
But even back then, she knew about learning. She was really interested in distributed systems, how a system could adapt. And she pursued some of that, but not as much. In those days, you couldn't really do learning systems that much. It wasn't popular. It wasn't the thing. And now it is. And so I think she's coming around and looking at how you do distributed learning systems in communications networks. And she's going to tell us something about it. Yeah.
Thank you, dear. So unlike most talks here at Tea Time, this is sort of a work in progress or just starting progress. Our funding just started at the beginning of May, so we haven't had a lot of time to look at it. I have 2 graduate students. This is funding from Amii. Thank you very much. 2 graduate students, Aidan Bush and Daniel Mitchell, each with expertise in one of the 2 aspects of this, namely looking at reinforcement learning applied to problems of network control. So one guy's more on the networking communication side, one guy's more on the learning side, but they're each learning about the domain that needs to be filled in. And right now they're trying to get up a simulation tool. Most of our work, I think, especially in the first year, and I hope that we'll get some decent results so that we'll be funded for follow-on, but most of it will be done through simulation. So that's kind of the primary thing, coming up to speed, understanding each other's domain where they're less well-versed, and bringing up the simulation tool. So first of all, what is a communications network? How many people know what they are? I mean, everybody uses them. That's a given. But how many people are familiar with them at all, about how they operate? So some guys, not too many though. So what is it? Well, it's a set of devices. Here's a pictorial representation of a very small one that enable end systems, things like your phone, sensors, web servers, blah, blah, whatever, to communicate among themselves and to do so cost effectively. You know, in the old days, before we had these things, if people wanted to talk between devices, supposing they had some big simulation they were running on a fancy computer somewhere, but they didn't have access to that locally, they'd make a telephone call into that computer to start things up. And that's fine, but if you think of all the billions of people that sit on the planet right now, if they all had to make point-to-point links with every place they wanted to go, that's kind of expensive and a silly way to do it. So you can, share the costs of these communications capabilities by making a kind of a mesh that will interconnect a whole bunch of people. And that's basically what a communications network is. So I've drawn lines here. It doesn't always have to be through a cable. It can be wireless. It can be wireless optical. It could be wireless radio frequency, microwave, blah, blah, blah. There's a whole bunch of different ways. But for now, I've just drawn these interconnections in this way. So it is inherently a distributed system. Each of these things, they're the end systems that would hang off the edges of these things. Maybe I should make a few here, little other things. There's maybe a couple of them up here. Maybe there's one over here somewhere. And there's some of these guys are only working inside the network itself, and some of them are the generators, the producers and consumers of traffic. So that could be your cell phone or your computer or something like that. So the network is made up of these things, the devices, the switching devices, the end systems, and possibly links between them. Could be fiber optic cables, could be Ethernet, could be anything. Okay. So decisions are made at each of these points here about where to send traffic. At the beginning, when you're sending it in, not much of a decision. It's more whether I should send traffic, not, you know, what I should do. But inside the network here, these guys are making decisions about where to send traffic based upon where the traffic ultimately needs to go. And that information is carried inside of the little packages of information. We call them packets. Okay, that says where they've come from, where they're going to go, how they should be handled. For example, video traffic would be handled differently. You might need a big fatter path to get that through if you're watching a movie than if you're just sending an email message. Some things need short delays. As you know, if you talk to guys on the phone and you're over a satellite link, you have a huge delay there that's very irritating. You think the guy isn't listening to you or he's cogitating over something you've said that's upset him. No, it's just an inherent delay. So there's things like that. Maybe you'd prefer, if you had a choice of a satellite connection versus something on the land that was a little bit shorter, you'd choose that for the delay reasons. So there's those sorts of things. Different things are going to have to be handled differently depending upon the sort of service you need that the applications are demanding. Okay. Now, they're also dynamic. So, yeah, these things might be stationary. They might move. A lot of my work had to do with cases where the whole set of networks moves. Users, the end systems, often move. The traffic patterns change over time. So that's dynamic. It's not always one guy, this guy sending to that guy, right? That isn't always the case. He may do that at certain times. Maybe he sends something at one time, he sends to these other guys. So those things change over time. Where it's going, what type of traffic it is. Certainly things can fail too. You can have a power failure that knocks out half of your network, or somebody digs up a fiber optic cable making a new apartment complex or something like that. Also, I mean, seriously, those things really do happen. I'm not making this up. So there's a lot of dynamism in the network. So it's a big distributed dynamic system, which is kind of an interesting thing. But there's even some other interesting things that I'm going to tell you about. So what did I mean? You guys all know what reinforcement learning is, but what did I mean by network control? Network control is basically any function that acts on these network devices, whether they're these guys or even the edge, the end systems, and may act on the little packages of information, the packets. It may even act at the signal level, which is below that level. And it's intended to affect basically, you know, where and when and how and what information is going to be sent in the network. And network control is a whole bunch of different algorithms that are going on in the network. It can be down at the level of signal processing all the way up to infrastructure design. You know, how do I, when I'm designing a network, maybe it's a metropolitan area network, maybe it's larger than that, how do I decide where I'm going to put switches, how much capacity these things have, what guys I need to connect together so that things are, you know, everybody can talk to each other. Do you have a reliability? If something fails, do I have alternate ways of getting to there? This isn't a very reliable network, but maybe the designer wasn't thinking so clearly when he did it. So that tells, the network control algorithms basically govern how the traffic is handled in the network, but at different levels. So there's the signal processing level all the way up to this sort of network design level. And they have different temporal, you know, network design. You don't redesign your network on the fly, usually. That's something that's done over a longer time period. Your signal processing is something you're doing in these tiny little periods of time. So things happen in that whole spectrum. Okay, so let me go to the next guy here. Okay, so what are, let me talk about one problem that's probably easy to relate to, a network control problem. It's sort of in the middle of things. It's one of my favorite problems too, so that's another reason to talk about it. And that's the routing problem. How do you figure out where things are going to go? So if this guy in the middle here, he receives something from here, and that something says, oh, I need to go to here, this guy has to decide, well, where is it I'm going to go? Well, in this case, let's just draw another line in here so we make it a little bit interesting. Okay. Where am I going to go? Am I going to go that way? Am I going to go that way? That's provided that he even knows about those sorts of things, right? So there are these decisions to make, and that's a control decision. Here's the traffic. It needs to be served in this way. It has to go to this destination. What choice do I make? Okay, so that's a type of control problem. That's not the one we're looking at, but that's one that has been looked at a lot, both in the networking context and even in the reinforcement learning context, which I'll speak about in a bit. God, I'm not going to have enough time for all this. Okay. So what are some of the challenges for network control, independent of whether there is any learning involved? Okay, you have to be able to define what the problem is to begin with. What is the thing you want to control? What are going to be your inputs to your problem? What are going to be your actions? What are going to be your policies? This all happens independent of whether reinforcement learning is in there, all right? Am I going to have a centralized decision making? Those of you who like software-defined networking would say, oh yes, of course I do. So is this a centralized algorithm? Is it a distributed algorithm? You know, is it decentralized? Maybe everybody does something, but they do it independently. Those sorts of decisions you have to decide. In this case, observations of your environment that go into your decision making are going to be partial. That's just how it is. That's real life, right? You're not going to have an up-to-date, accurate, total view of everything that's going on here. Okay, that's it. That's a given. So you'll only have partial information, but you're going to have to be making some decision. You also have delays. So where did the delays come from? Okay, they come from speed of light. We can't change that, right? Something goes from here to there. We can't just say, okay, that's 0 seconds. No, it's not. They're there. So the more hops you have, the more you have those. Their capabilities of these switches here, maybe they can only switch at certain speeds or send things out at certain speeds. That's a limitation. So you're going to have delays. So if you need, let's say this guy needs some information about this other part of the network so he can figure out where he's going to send it. To get that information to him, it's not like he has some God view of the network. That has to go somewhere. So there are delays in getting your information that you need to act on. Anybody has any questions along the way, they should just ask me, because I know this is a different domain than a lot of you guys do. Okay, what else? Oh, yeah. So what you observe too might have some errors in it. They're noisy things. There's things that you measure about the network. You know, there are things like receive signal strength, and a lot of these, okay, that may mean nothing to you, but there are things that you can measure about your network that what you see about it might not actually be correct. It's sort of okay, but there can be noise in it. So that's another thing that's in there. And finally, you have all of these. Yes, sir.
Do you ever consider that, maybe, certainly when we're talking about something as large as the internet,
yeah,
no one company owns all of it.
Yeah.
Do I worry that there are some of the other players in the space aren't cooperating?
Yes, you do. Yes, you do. And that's part of the big picture. Sure, yeah.
So it might be they're feeding me information about other parts of the
That
network.
isn't right.
Maybe
That's right.
That's
Mike, you make everything into a game.
I know he does. I was thinking that myself, but
everything is a game.
so that is an issue. But for us, when I'm going to tell you about our specific problem, which I haven't even gotten to, and I've already spent God knows how much time. Okay, yes.
So I just want to say that you've discussed all these things like incomplete knowledge and delays.
Yeah.
And noisy and
I have one more thing to discuss, though, but go ahead.
And this sounds like what the AI problem.
It is. It's a great problem. See, I feel like, okay, games guys, don't kill me, but I feel like you have these environments which are these perfect things, and you have all of this knowledge, and everything is nice and clean. The learning problem is tough enough in there, but then when you throw all this crap in, then you have even more of a situation. So that's one reason I encourage anybody working on reinforcement learning to look at a little bit messier problems than you guys have. Because at the beginning, you want to just make sure your learning algorithms are working right. So you don't want to put a whole lot of mess in there, because just trying to figure out what's going on, you don't know if it's caused by this, that underneath. But now that the algorithms people are getting more and more experience with them, you kind of get a flavor of how they're going. Then you can start to mess up things like what you observe about your environment and see what happens. And as I say, the delays are there. It's not only like in your cases of delayed reward, where an action you take here may have ramifications long ago, which you have to get it back, but you just have these intrinsic delays that are part of just getting information about your network. And the last thing is you have all of these controllers going on at the same time. Algorithms. There's things operating in the signals, there's things in the routing, there's things, when do I send this, blah, 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 scheduling sorts of issues. All of these things are going on. And I'm going to digress just slightly, but for those of you who have studied networks, there used to be this layering thing that everybody was all excited about. And I think that has caused a huge problem in how we think about network control, because that caused people to mentally compartmentalize what they thought was going on in the network. And they said, oh, I can just flip this control algorithm at this layer in for another one, and I don't even have to worry. Well, of course, there are all these interactions about what you do somewhere has ramifications in other places. And unless you understand that, you are going to make giant mistakes, and many, as we say, mistakes were made. So that's something that it's a problem. Trying to figure this out as solve it as a giant multi-part control problem with all these different controllers operating at different time scales and spatial scales and everything else. You don't want to do that, but you still want to be cognizant that the problem is there. And I think if you think more about the network as a set of different control problems that have to be solved, you're not going to solve it as some monolithic thing either. It's just too big that way. You can't do that. But to think about that, when you change something, what are the ramifications of something else? I think that's something really good to do. And I really am going to run out of time. Okay, what's my next thing? Okay, so when you're designing a control algorithm, you have to think about what are the locality of the observations that you're going to use as your input, all right? And that's temporal as well as spatial. So, do I need things that are very much in the recent past, or do I need something from longer ago as well? Do I just need it from my neighbors, or do I need to see larger parts of the network? When I take an action, how long does that persist? Does it persist, just for a short period of time? Does it persist for a long time? Does it affect just my neighbors, just me? Does it affect the whole network? All of those things have to go into it. Where the decision making happens, these software-defined networking guys would like to have it done in a, I'm sorry, Amir, I keep picking on you, but this is one of those things that I love to hate. They want it in a centralized place. I get this beautiful view, this perfect view of the network, and then I do this giant optimization problem in a centralized place, and then I put what actions? I put the policies in here, but these guys have no say about the policies. They just act on them. That is not how I would design a network. I want all of these guys to be smart, but they're only sort of locally smart. They know little things, but everybody's going to be acting alone. If you make a decision here, something happens here that you need to react to. You want to be able to do that here. You don't want to send it to God and then have God come back and tell you what to do. No, you want to make the decision here. And so that's sort of the flavor of things that I think we're going to go to. In the past, a lot of the algorithms in the network are already adaptive. So it isn't like we're saying, oh, let's start to do adaptive things. No, few things are fixed, but a lot of it's adaptive. But the adaptive algorithm itself has been designed by engineers like me, right? So we say, well, I think I understand, how these channels work and what happens when this happens and that happens. And this is the type of, say, feedback control algorithm that I'm going to put in here. But as we know from things like AlphaGo or the Atari games, right? What we think of are good ideas for doing something may not be the best ideas. The features that we think are important to use as our input, they might not be the best ones to use. And so I think that one of the main things that we're going to be able to get out of looking at reinforcement learning here is designing, better control algorithms here and learning of features. What's important? Now, not easy. It's nice to say these things, but this is going to give us, more, I think, agility in here. We'll be able to be more robust to things that happen. We'll be more efficient. And our networks, if we do these things right, are going to cost less to begin with, which is another thing. I mean, there's real-world things we have to worry about. But not only will the performance be better because we can make these decisions and not have these sort of human biases. When we design something, we have these human biases. Well, this is the way these guys used to do it, so I'm going to do it that way too. No. If you have your, you allow your algorithms to figure things out, it's going to be a better thing. I don't have much time, do I? What do I have? Like 5 minutes, 4 minutes, 3 minutes?
7 minutes.
Oh, good. Oh, thank you. Oh, I just touched my microphone too. Okay, sorry about that. So what if we do put, okay, reinforcement learning has actually been applied in network control. And so it's not a new thing. You know, you might think it's a new thing. And a lot of people that are publishing don't realize what happened, 40 years ago or 50 years ago, whenever. The earliest I know of was in the 1970s, and that was Narendra and Wright. And they looked at using a type of reinforcement learning-based algorithm learning automata. Do you guys know about those at all? Some guys know. Okay, so basically I'm just going to say there are many variants of them, but basically what it does is it increases the probability of taking an action that has done a good thing, and it reduces the probability of the other possible actions you could take accordingly so that they all have to win. But basically, there's a bunch of different variations on a thing, but that's basically how learning automata work. And they used it for routing in telephone networks, which is a little bit different from this because often you only had two alternate choices. I think telephone networks are different now, but back in the 70s, it was a little bit different network structure than the packet switching networks. And it actually worked pretty well. This was back in 77 or something like this, so it was a long time ago. Then there's like these little spotty things here and there where people did routing. In fact, there's a Swedish guy, Jakob Karlström, who did a whole thesis on reinforcement learning for routing problem as well as admission control. When do you allow stuff to come into the network? Beyond that, there are things here and there, sporadic sorts of things, but nobody ever really sat down and said, okay, what are we going to do? Does this make sense? Oh, it was either learning guys that didn't know about networks saying, let's put this in here, so that they didn't always make perhaps the best choice of comparison points between the existing networking technology and what their learning algorithms were, or it's networking guys going, oh, I just read about Q-learning. Maybe I'll throw that in my network. It's a little. I don't want to dismiss these efforts because it's always good to do these things, but I feel like you need to have a little bit more thought about exactly what sorts of algorithms you're going to apply to these particular types of problems. Now, the one, I don't hardly have any time now. What do I have? I do. Oh, great. Okay. So let me say a few other things. And I was definitely guilty of this. Learning is perceived as a slow process, and it is, particularly trial and error sorts of types of learning. So that's one reason, as well as, people weren't really into that sort of learning, even in the machine learning area. They don't want to do supervised learning, they don't want to do reinforcement learning. But the other thing is that it's perceived as slow, and you think, this network has got to do these things. It's how many packets is going to drop on the floor before it gets the thing right. So that's one thing. And another thing is, we talked a little bit, there wasn't all that much cross-fertilization between the networking and learning communities. So things like this RLDM conference that's coming up soon, I think, is a good way to sort of help that. So there's challenges here. How are you going to cast these things as reinforcement learning problems, these little adaptive control problems? What are your rewards? What are your actions? What are your observations going to be? All of those things are sort of non-trivial when we start to look at these problems, because if you make the wrong choices, that could be an issue. Hopefully we're going to learn features, so that will help. But still, what's the space of the observations? What can we observe about the network that we're going to put in there? It's a huge space. It's a huge space. The choice of actions is also huge. So we need to really think about it when we're going to apply these two particular problems, what we're going to do. I'm not going to talk about that one. The particular problem that I decided on looking at was congestion control. So what is congestion? Do you guys drive cars at all? Do any of you drive cars? Okay. Do you ever go across Grote Road in its current state during rush hour? Okay. So what happens when you have more demand for service for something than the rate of that demand exceeds the rate of the service of that thing? Well, giant traffic jams. And they back up and they back up. And that can happen in communications networks. Supposing that a whole bunch of guys are sending all sorts of stuff into this poor guy, and they all somehow want to go here, okay? Well, this link may not be able to carry all of that traffic. So you start to get queues building up back here, packets trying to go in there. And, you know, it's not infinite memory in these switches. What are you going to do? Some of that, if more stuff comes in, it's not like, you know, on a highway, you know, there's not helicopters pulling cars off and saying, oh, that's too much. You know, it's not like that. So, but here, this guy can say, there's no space, that packet's gone. But again, that packet is taken, wherever it came from in the network, it's taken all that effort to get there. So you don't really want to be dropping things, right? But then this problem can spread. These guys all of a sudden get backed up because they can't put stuff in there, so they have to hold things in their queues, and it can be a huge disaster. Oh, okay. Yeah. So,
what would the actions be for the congestion control?
well, may you ask. The way the standards go on the internet were actually sort of developed after a lot of other people had looked at congestion control, but they only govern the rate of entry of traffic here. Now, talk about features that were not perhaps selected well. The way that congestion was detected was if a packet is dropped in my network, that means that it must be because of buffer overflow and there's congestion. Okay, so the way they do it, they ran an algorithm that required every time you sent something to get an acknowledgement back, and if you didn't get an acknowledgement back, you assumed the packet was dropped, and therefore, well, particularly those who talk in wire, okay, I really will. In wireless communication, you can have interference happening in your network, right? So that can cause you to lose packets all over the place. There's other things that could happen. Maybe there's a lightning strike and zzz, you know, you have a little problem. You get errors in your packets. So a loss of a packet does not necessarily mean congestion at all. But that was then causing people to start reducing their rate. So right now, the simplest case, but not the best case, I would say, is to do it at the end, control the rate in, and then you have to take a signal of what is congestion. Now that's another question, right? What I want to do is what I did ages ago, but you know, I'm going to revisit it now, and you actually look inside the network here. So these guys have some smarts about what's going on. They know about how much traffic is at least the demand locally on them and what's happening here. And they can tell things to their neighbors. They can tell things to these guys to do it. So that's one thing. Eventually there will be a rate reduction, but the other thing is that perhaps doing that, you know, you have no congestion in your network if you don't send any traffic, right? So you could reduce the rate and say, I'm never going to be congested, but yet you're never getting, excuse me, enough stuff through the network, as much stuff through the network as you could be. So another thing is also to take split the traffic. If you have alternate ways of getting to that point, maybe this is a better way to do it too, so you're not even dropping something. And even guys back behind you don't even have to know. Now, initially the way we're going to look at it is only as a rate that you adjust, only as a rate. Who you tell, that's another question. That's part of the action. But later on, we're going to look at alternate things like this, okay? So there are congestion control algorithms that do this out there. They're not the standard ones in the internet. We don't want to be bound by the standard. I'm done. No, I'm not quite done, but I'm very close to done. We don't want to be bound by the standard. So what we're thinking about is how would I want to solve this control problem ideally? And then, you know, how am I going to use reinforcement learning most effectively to do it? In the worst case, we find, you know, our engineered solutions are really good and we really can't do better. But I really think, particularly with the feature learning stuff, what constitutes congestion? When should I start to take these actions that will try to alleviate that? I think that could be a big payoff, because I've learned from commercial service providers that congestion is an issue, and they often don't find it about it. Even though there's guys at these what they call network monitoring centers that are paying attention to stuff, they get phone calls from irate customers. My stuff isn't getting through. What's wrong with you guys? That's when they learn about it, and they don't like to learn that because customers walk if they get bad service and they're paying for better. So that's what we're planning to do, what we're starting to do, but we haven't done it yet, and maybe later I will be able to tell you what that is. Okay, thanks guys. Sorry. Oh, sorry, yeah.
So you talked about what and why.
Yeah.
Can you tell us a little bit about how?
How we're going to do, how we're going to do what?
Are you going to build a network? Are you going to work with Huawei? Are you going to build a simulation?
Actually, I did mention it at the beginning, but it probably just went. At the beginning, we're looking at simulations. And the reason why is because we get to control everything that way. We also are not looking at giant networks. We have to figure out what's going on. If you start to have this giant space that you're working with, it's going to be really difficult to figure out why certain behaviors are happening. So we're starting small with a simulation. Later on, it would be great to work with a real network such as Huawei's. Let me back out of that a little bit, though. We would likely be confined to working with standard protocols, so we would need to see how well we could do with those standard protocols, which may be very different than what we do here. If we had a play network where we were allowed to put our own stuff in of anything, that would be great, but I don't think that will happen. But yeah.
I guess this is more about the specifics of the networks that you're looking at. Since there's lots of congestion, are the things that the data that's causing the most congestion are data that you're okay with dropping packets like video?
Well, it depends also on dropping, even the distribution of the drops, right? So there's different things. If you look at an average drop rate, you can say, well, these guys have the same loss rate, but maybe if it comes in big chunks versus intermittently, it's going to be very different for the user's experience with whatever that he's receiving. So that's an issue. But the problem is in some networks nowadays, because you can pump stuff in so fast, that you could go from a non-congested state to a congested state really quickly. In the past, it used to be slower, so you could see things building up and you wouldn't lose that much stuff. Now you can lose a whole bunch of stuff, or a guy's going to see a disruption. So it may be that we find that there's nothing we're going to be able to observe about them, or no good features that are going to have us be able to predict this sooner than we can. But maybe the choices of how we act about it afterwards, and massage those, what we learn to do once it is detected, that may be a thing that we'll be able to do better than we do now. Yeah.
You talked about sending messages to the neighboring nodes.
Yeah.
Does that use the same channel?
Oh yeah. So that's a thing. Like a lot of people, you see a conventional algorithm in a communications conference. Assume I have perfect information about my whole giant network, about everything that goes on. Well, how are they getting that information? It has to come in band, right? And then you can have more of that stuff. In the silly case, you would have more of that stuff. If it's a very dynamic network, you're going to have to be updating the state information all the time, and it gets to be that's the majority of the traffic rather than the data. No, seriously, right? Yeah.
So you said this is a distributed system with distributed observations and actions.
Yeah.
What about the reward structure? Is the reward individual per node?
Yeah, I think it is. It's not one of these. That's something I want to talk about, but I had to stop. So the distributed aspect of it, everybody's going to be acting independently, but one of the things that we do want to look at is how much information we have to share here. The rewards, probably not, although they may get the same information back. If it has to do with throughput to certain destinations or things like that, we haven't decided exactly. There's a bunch of different ways to reward, so we haven't even decided what we're going to do yet. For sure. But if we do, it's not like one of these multi-agent systems where they're all going on that focused on the thing. It's not like that. They may have similar objectives, but they are like little guys operating independent. Yeah.
So if they all have independent rewards, how will you assess the quality of the network as a whole?
Well, what the thing is that you have all these different flows going there. So how I will assess it is how well they did. That's, they're having their own assessment of it through their reward signal. But for me, I'll say, is 99% of my traffic getting through with a quality of service that it needs to? I'll go, yes, it's done very well. So that's an independent thing, but not just reward based. That's me looking down on top. Yeah. Sorry, there's another. Janie. Some topologies would be easier to control, but in the real world, what happens is you are constrained by where you can put your switches, okay? You're constrained by where you can lay your fiber optic cable. If there are all of these constraints, and they have nothing, that's, I own this land, you own that, that sort of a thing. Where can I put my cell tower? Not everybody wants one in their backyard, right? Maybe my backyard is the greatest place in Edmonton to put one, but I'm not putting, it's not going up there. So you have these kind of real world constraints, but yes, certainly the topology can change. In a mobile network, that's where every switch is mobile. We're not looking at wireless of that type of network to begin with, because there's more issues there. But when you look at this, certainly you could arrange yourself to deal with topographic features and things like that are there so that your signals aren't going to be blocked. Yes, there certainly are, but you're usually given a network structure in the fixed case, and you need to work with whatever you're given.
Last question?
So if all your algorithms fail at this, maybe we can build a good challenge problem out of it. Instead of outperforming over-engineered solutions, it could in itself be a good way to develop new algorithms.
I'm hoping that things like this, when you work in these types of environments, will sort of tweak reinforcement learning guys' brains and say, oh, you know, that's a problem that we've thought about. We haven't really been able to, haven't confronted it so directly, and we will in this environment. It might give you some insights about things to go. So certainly, yeah, that's what I'm hoping. I think it's easier to get the networking guys interested in putting learning in right now than it is to get the learning guys to do networking, but I'm hoping to change that through things like this. Okay, thank you.
We got separate wars. It really is like the multi-agent thing. And then you win. Yeah.